Hey everyone, looking at 8.4, the laws of logarithms. And we're going to go through a couple of points first before we get to the actual laws below. So first things first, we know that the exponential equations look like this, where they're always above the y-axis. So if I was to write the equation for that, y is equal to, let's say, a to the power of x. We know that the y values are always going to be greater than 0, and that's what it says here. The range of the exponential function is y is greater than 0. They're bigger than 0. So how does that relate to when it's written in log form? If I was to take that exponential equation and write it in log form, it would look like this. Log a, because that's the base, x is the exponent, and y is the argument. That's the equation. Now, we said that y is always greater than 0, and that's going to be true when we're writing equations in log form. The argument has to always be greater than 0. If it's a negative value, we cannot evaluate it. So there is no answer to a question like x is equal to log of -2. Can't solve that. Why? Well, remember this is a natural log, 10. So we're saying 10 to the power of x is equal to -2. Can't get an exponent on 10 that would give us a negative number, let alone -2. So we can't get anything like that. So it has to be greater than 0. You can also not have an argument that is equal to 0. So if this was 0 here, you can't have 10 to the power of x equal to 0. There is no exponent that will give us 0 as the answer. So the y value, the argument, can never be 0. Or negative, has to be a positive number. So that being said, another thing that's true, so I'm just going to take this off so there's less on here. But another thing that's true is that the base is always going to be greater than 0 as well for logarithms. That a value here. We're not going to have negatives down there. We're not going to have 0. It wouldn't make sense to have 0 as the base because then we'd have something like 0 to the power of x is equal to y. So it wouldn't matter what anything else is. It would all be 0 if we had a base of 0. So, and then it would be linear, so that wouldn't make sense. So that's kind of how those ones work out. So we'll look at these laws down below here. So you might remember these, the product rule, which said if we're multiplying two powers with the same base, right, that a, we're multiplying those, we add the exponents together. That was a rule that you learned back in grade 9. Now we have one for our logarithms. Now, if we kind of evaluate what we got here, basically, remember, logarithms work with the exponents. So look at what's happening over here. We're multiplying these exponents, and it results in an addition. So what does that mean? Well, that means that if we have a log with a base of, let's call it a, to an argument of m, and we add that to log with the same base with an argument of n, we'll call it, that's equivalent to log of base a m times n, a multiplication. That's the first rule, right? We're adding two exponents, results in a multiplication of the argument. I'll post proofs of these as well so you can have a look at them. Same goes for the next one. So we have a division happening here, results in a subtraction of the exponent. So very similar to the one that we have above. The only difference is log am minus log an. That's equal to log a m over n, or m divided by n. Same idea, same rules that we saw. Once again, I'm going to post proofs to these if you're interested in it as well. And the last one, the power rule. Basically what happened here was if we had a to the power of x raised to the exponent of y, that was just the result of the multiplication of the exponents. So how does that apply to the logs? Well, in this case, if we have log a of m to the power of n, something like that, that's equivalent to n log am. Right, so that n just comes out front. It's the power of a power rule. If we have an exponent of n on our argument, it can come out to the front. Once again, I'm going to post proofs of each of these ones. It's a little bit longer to go through if you're interested afterwards. But let's go through these. Let's evaluate. That's one of the rules is keep in mind they have to have the same base. Just like they did in grade 9, grade 10, they have to have the same base. Or grade 12, they have to have the same base. Doesn't matter what grade, they have to have the same base. So first one here, simplify and then evaluate. So simplify means write as a single log. So these have the same base of 4. So that's good. Our answer is going to be log 4 of. Now my arguments are 8 and 32, and we're adding them together. So it's going to be 8 times 32. So when I evaluate log 4, 8 times 32, that's going to be my new argument that we have here. So 8 times 32 gives me 256. So let's try to evaluate this. So I'm going to say this is all equal to, let's call it y. So we're going to have 4 to the power of y is equal to 256. And then remember how we solve these, we need to get the same base on both sides. When I do that, we end up with 4 to the power of y is equal to 4 to the power of 4. Therefore, y must be equal to 4 because we're equating those exponents together, 4 and y. All right, let's keep going. Same idea for the one over here. Both have base of 4, so log 4, and we're going to be multiplying together. 80 times 5, that's going to give me my new base. And we end up with 400. Now, if I'm trying to evaluate this one here, we have 4 to the power of y, because we'll call all this equal to y, is equal to 400. And we can look at that and say, well, I'm going to try to solve this one, but I can't think of a number that nicely goes into both those ones. If not, I can use trial and error maybe. But for this one, you might remember that earlier I mentioned there's a little bit of a shortcut that I'm going to get to later on for evaluating logarithms don't have the same or a common base of 10. We can make that log 400 divided by log 4. And we would get 4 to the power of 4.32 is equal to 400. So therefore that must be the exponent. Y is equal to 4.32. Whether I'm using trial and error and I come up with 4.32, or I use that shortcut of getting the natural log as well, that we'll get to a little bit later on in this section. But that's the shortcut for it. All right, let's keep going here. I want to evaluate log 515 plus log 520 minus log 512. Well, the first part is an addition, so I know it's going to be log 5. We're adding 15 and 20, which means that we're multiplying them together. Then I'm subtracting 12, which means I'm dividing by 12 when I combine them together. That's the laws of logarithms. So I need to find out what my new argument is, that section that's in the brackets. So 15 times 20 divided by 12 gives me 25. So I have log 5, 25. Right, that's equivalent to all of this here. Log 5, 25. Now I want to evaluate this. So let's suppose I'm going to call it y, whatever I evaluate it as. So that's 5 to the power of y is equal to 25. I get common bases. 5 to the power of 2 is 25, so I know y must be equal to 2. And we'll keep going here. The last one here. This one we don't have anything to simplify, but we'll call it y. Now if I want to evaluate this, I'm going to have 16 to the power of y is equal to 4. So you might look at that and say, well, if I want to have the common base, I know that 16 to the power of negative a half, or to a positive half, not a negative a half, I don't know where I got that from, is equal to 4, right? These are equivalent. All I do is rewrite base 4, or 4 as a base 16, right? Square root of 16 is 4. That's all it's saying. Square root exponent is a half. So therefore, y is equal to a half in this case. All right, let's keep going. Given log b, rewrite in terms of log bx. So what do I do here? We know that this part here, the square root, means that it all has an exponent of a half. So I know that we have log b x squared times z all over y, all of that to the power of y to the power of 3, all of that power of half, right? That's what square root is. So I'm going to apply this to each of them that are inside. Log b, the half, when we have an exponent, it applies to every single variable inside. So we're going to have x, which had an exponent of 2, times a half, which is 1. Z to the power of a half, all over y, 3 over 2. So we can write it like this. I can also bring the y up if we want to write it as a negative exponent. We'll have x, y to the negative 3 over 2, because that's just on the y, z to a half. Right, so we have lots of different ways that we can evaluate what we've got here, or express what we've got here. All would be fine. All right, keep going here. All right, so for this next one too, it says express each side as a single log, then solve for x. It's a little bit of a typo here. It should say log x. Okay, that's base 10. To log 4, right, that's also base 10, plus 3 log base 10, 3. So we might look at this and say, well, I can't do much on the left side. The right side, we have 2 log 4s and 3 log 3s, but I can't add those together because they're both not the same. Those are not like terms. I can't add log 4 and log 3 together. It's like adding x to the power of 2 and x to the power of 3 together, or x to the power of 3 and x to the power of 4 together. We can't do that. So I have to evaluate this or simplify it a little bit. One of the laws that we learned earlier was that if there's an exponent on top, 3 for example, it can come out front. Well, we can do the opposite with that. We can take this 2 and bring it up top. So I'm going to write this as log 4 to the power of 2 plus log 3 to the power of 3. Right? That power of power rule said that exponent come down. Well, it can go right back up where it came from. So now I can evaluate those. Log x is equal to log 16 plus log 27, because 3 to the power of 3 is 27. And now I can use that product rule that says if I'm adding logs together, I can multiply their arguments. Right? Arguments are the numbers that are with it. 16 times 27. Log x is equal to log, and I get my calculator, and I put in 16 times 27, and we get 432. So if I look at the left and right side, I'm just going to make them equal where they are. So x must be equal to 432. So in that expression above, when x is 432, it's the left and right side are the same. So let's keep going here. Next one, we have log 7s. So this left side, we can't do too much with it. Log base 7x is equal to, if we look at this and we see, well, I have log 725 and log 75. Can't subtract those, right? I have 2 of them, but I can't subtract them because they're not the same. So what I'm going to do is what we just did. Log 725 to the power of 2 minus log 7 5 to the power of 2. Right, that 7's always going to stay a 7. It's not going to change, not going anywhere. So when I put my calculator, 25 to the power of 2, we end up getting 625 minus log 7 5 to the power of 2 is 25. And we keep going. We're subtracting those two logs together with the same base. So that means I can divide their arguments. Log 7, 625 over 25. Log 7x is equal to log 7. 25 divided by, or 625 divided by 25. We just did that one before, so we know that it's going to work out to be 25. And I look at the left and right side and say, well, I equate them. Well, this x is in the spot that 25 is in on the right side. So x must be equal to 25 because everything else is equal. And we solved for the left and right side. So that's this section here. One thing that we will be talking about, it's in the next section, I thought it was in this one when I mentioned it earlier, is that how do we deal with things like log 4, 10? How do I evaluate something like that? Well, in the next section, we're going to learn about log 10 divided by log 4. We use the principles that we just kind of talked about, but we'll be going through it shortly. So that's how you can evaluate these ones without having to use trial and error. Because normally you'd say, well, 4 to the power of y is equal to 10. And you'd start putting in numbers, 4 to the power of different values to try to get 10. But to cut down the work that you do and the trial and error work that you do, that's the rule for it. That's how we get a common log. And I'll explain that shortly. And I had mentioned it earlier that we're going to talk about it, but it is in the next section. So that's that one. There's a few questions for you to try working on these laws. I'll post the proofs to those laws as well if that's something you're interested in. If not, as long as you know these laws that are up here, you'll be fine. It's a little bit difficult to work with at the beginning, but with practice becomes a lot easier. And if you have any questions, let me know. I'll talk to you soon.